So let's talk about inserting into a heap. At its broadest sense, this is a two-step procedure. Now, some of those steps have many sub-steps, but we'll get there. So let's talk about the two-step procedure. We first insert a new node while keeping the tree complete. And then we restore a heap order property via upheap bubbling. That's it. Okay, so let's break these down. Insert a new node while keeping the tree complete. How do we do this? Well, I was doing this when I was just drawing my trees this whole time, right? I'm inserting new nodes constantly while making sure that the tree stays complete. How am I doing this? Well, we either need to go to the next available spot, the leftmost empty spot at the lowest level. This one's getting a little out of whack, but you can see what's happening. And then once we get here, we've got no more spots on the lowest level that are available, so we move to the leftmost spot of the leftmost leaf. That's it. That's how we do it. That's how we insert. So if this were the heap, this is the new guy. So, okay, now what do we do? Well, we have to restore our order via upheap bubbling. Why? Well, what if this node here has the lowest ordering value in the entire heap? That should be at the root, but it's not at the root, so it's not a heap anymore. So we need to make sure that we get back into that heap order. And this is how we do it. Upheaping is designed to restore the heap order property. So what do? We start with our newly inserted node, and while the current node is not the root, why? You can't go any further. Root doesn't have a parent, so there's no point in comparing. While the current node is not the root, and the relationship between the current node and its parent violates the heap order property, we're going to swap the data from the current node and its parent, and then we're going to move the current node to the current node's parent, and we're going to repeat the process. Some examples. Here is a min heap, and you can tell it's a min heap because 4 is less than 7 and 5, 7 is less than or equal to 11 and 7, 5 is less than or equal to 6 and 8. It's a complete tree. Beautiful. So if we insert another 6 into this heap, how do we do it? Well, the lowest level is full, so we have to add it as the left child of the leftmost leaf. And now we upheap. We compare 6 and 11. Is 6 less than 11? Yes. Swap. We compare 6 and 7 because 6 is not the root. Is 6 less than 7? Yes, so we swap. Now, is 6 the root yet? No, so we compare it with 4. Is 6 less than 4? No, so we're done, right? And remember, once again, I want to repeat, each of these are the ordering value. They could have an associated value with them, right? We are only showing the ordering aspect, which is driving our behavior. So we're done, right? We've got our min heap, we're back. So let's do this again. Let's do this with 1. If you want to try it on your own, please do. Pause the video. Okay, so where do we add it? The leftmost available child, which is here. Okay. 1 and 7, we compare them because 1 is not the root. We compare them, 7 is bigger, so 1 comes up here. We do it again, do the same process, compare. 1 is smaller, so 6 comes down here. 1 comes up here. Do it again, compare. 1 is smaller. Swap, 4 comes down here. Do it again. Oh, we're at the root. We stop. There you go. this is it. The process isn't complicated, but it does have some steps. Okay, and it's critical because if we add 1 down here, right? If 1 is here, this is not a heap. The heap ordering property is violated in this subtree. So we need to get it back into the proper order.